Algebra 2, Concept 20, Part A, Graphing Radical Functions. What's going to be most helpful in this concept is to become familiar with some parent functions. We're going to be looking at the square root function, so you can see that on the left, f of x equals the square root of x, and the parent cube root function, f of x equals the cube root of x. So to get a picture of this graph, let's plot some points. And of course, we want to make our life easier, and I'm sure you do too, when you plot some points. So let's put in to the equation on the left some perfect squares for x. Let's start with 0. And then I'm thinking positive numbers because I can't put in negatives because those will give me real or imaginary numbers. So my next perfect square is 1, and then 4, and then 9. So now I'll take the square root of each of those. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, and the square root of 9 is 3. Now let's graph this, and I'm going to go off graph space a little bit, but I've got the points 0, 0, 1, 1, 4, 2, and 9, 3 would be off graph, but 3 points is enough. Now this graph has a definite starting point. I'm not going to graph it into the negatives because I can't take the square root of a negative number and get a real number. So my starting point is at 0, 0, and then it will continue off to the right, and so you can put an arrowhead at the end. So remember, the domain is a description of the x values that are used in this function, and because it has a starting point, the only x values that are being used are the ones that are greater than or equal to 0. So that's how you need to write your domain. For your range, that's all of the y values that are used to graph this curve. So that is also all the y values that are greater than or equal to 0. So square root functions have limited domain and range. Now, soak that in and just become familiar with the shape of that graph. All right, let's move over to the cube root function. So we're going to plug some points in. Now we're going to think of perfect cubes. Well, 0 is a perfect cube, and then numbers greater than 0, I have positive 1 and 8, and then let's graph into the negatives because we can take the cube root of negative numbers. So let's do negative 1 and negative 8. We'll not be able to graph our points with negative 8 and 8 because it'll be off graph, but 3 points will be enough. So the cube root of negative 8 is negative 2, negative 1 is negative 1, the cube root of 0 is 0, cube root of 1 is 1, and the cube root of 8 is 2. So that's where those values come from. Now let's plot those points. So I'm going to start with 0, 0, 1, 1, and negative 1, negative 1. If I graphed the remaining 2 points, my graph would look like this. I think of this as like a little propeller motion. So notice it starts down on the left and then increases as it moves to the right, and it does a little jig-jog in the middle. All of the x values, positive, 0, negative, can be used, and as well as the y. So our domain is all real numbers, and our range is also all real numbers. Now you're going to use your knowledge of those parent functions to graph transformations. Let's talk about transformations and get some examples. So horizontal transformation is when we have a value in the equation that's added or subtracted to the x underneath the the root. So an example that you could write down is f of x equals the square root of x minus 5, and that will shift it. If you remember, it's going to shift it opposite of what you would think to the right 5. Now let's get down a cube root example. And let's make a generalization that if we subtract an h value, it shifts our graph to the right. F of x equals the square root of x plus 7. So notice our values, that value's underneath the root symbol. That's going to shift that graph to the left 7. So if we add h values under the root, then it shifts to the left, just like with other functions. Vertical translations up or down. So if we add a value outside of the root function, or in this case subtract, it will move the graph down. And then if we add, so let's use cube root of x and plus 2, that will move the graph up. So generalization is that if you subtract a k value, it moves the graph down, and if you add a k value, it moves the graph up. Now let's talk about reflections. So this is if we have a negative multiplying outside either our square root or our cube root function. That will reflect or flip the graph over the x-axis. So rather than starting down on the left, up on the right, it will start up on the left and then continue down on the right. And then finally, a horizontal stretch or compress. Sometimes you'll see that called a shrink. So that's when we have a value multiplying on the outside of the root. So 5 times the square root of x, that would be a stretch by 5. If the number is greater than 1, you will have a stretch, and that will make the graph go up. If you have a value that's less than 1, that will be what we call a compress, and that narrows the graph, or it brings it down towards the x-axis. And then notice that that value also needs to be positive. So if that a value is less than 1 and at the same time greater than 0. All right, now let's use these transformation generalizations and our knowledge of the parent graphs to graph these transformations. So notice we have a square root function that's been transformed, x minus 3 plus 1. So let's identify those transformations. The minus 3 will shift it 3 to the right, and the plus 1 will shift it up 1. Now remember, in the square root function, those values from the parent function, those points, we had 0, 0, let's graph them, 1, 1, and then the point 4, 2. And then let's go ahead and draw. So this is the parent function. Once you get that down, then you can easily do the shift with each of those points. So in red, I'm going to shift each point to the right 3 and up 1. Well, I can shift the first 2. I always work left to right with my points, so I don't lose track of the ones that I've shifted. So now our final transformation here and graph is the one in red. For our domain and range, look at the red function and notice which x values are being used. Those are the ones that start where x is 3 and continue into the positive values. So our domain is x's that are greater than or equal to 3. Notice that our range for the y values of the curve start where y is positive 1. So the range are all the y values that are greater than or equal to 1. And those do correspond with our h and our k values in the equation. Let's try another one. Notice we've switched to a cube root function, so you're going to need to switch your parent function in your mind. And let's identify the transformation. That's going to be a shift left 2 because that number is underneath the root. Now remember those basic points from the parent cube root function. So we graphed 0, 0, 1, 1, negative 1, negative 1. And then go ahead and draw your curve. So this is the parent function. Now I'm going to, in red, shift each of those points to the left 2 and draw that transformed curve. If you look across the x-axis, you'll see there's no break in the action. So that means all of the x values, negative, 0, and positive, are being used, all real numbers. And that is the same for our y values. So our domain and range are both all real numbers. All right, now please pause your video and try the independent practice problems and then come back and check your work. All right, welcome back. So for the first problem, you should have realized that this graph will shift down 2, and this is a square root function, so you'll take each of those points from the parent function and shift them down 2. For your domain, you should get that all the x values that are greater than or equal to 0 are being used, and for the range, it's all the y values that are greater than or equal to negative 2. For this problem, it's a cube root, and you should have noticed that the transformed graph will shift 1 to the right and 3 up. So taking that parent graph, you're going to shift each of those points to the right 1 and up 3. Our domain and range for the cube root function, even transformed, will still be all real numbers. All right, and that concludes the notes for this concept.